Hello, welcome back for lesson 5.2. We are going to learn about the mean, variance, standard deviation, and expectation. The expected value is often referred to as the long-term average or mean. This means that over the long term of doing an experiment over and over, you would expect this average. It is the same process as calculating the weighted average for grouped data. So this should look very familiar. A men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5. And the probability that they play 2 days is 0.3. Find the long-term average or expected value of the number of days per week the men's soccer team plays soccer. To do the problem, first, let the random variable x be the number of days the men's soccer team plays. So x takes on the values of 0, 1, and 2. Notice I have those in the table here. So this would be like your x1 column in Desmos. Construct a PDF table adding a column for the product. So first, the probabilities from what they told us, I labeled here. This is going to go in your y1 column in Desmos. To find the expected value on average of lots of soccer teams, like going week after week after week after week, using the likelihood that they practiced or played on these days of week, we would multiply those outcomes times the probability and add them. So when we find their products, we add 0, 0.5, and 0.6 to get 1.1. So the expected value is 1.1. And we would describe it as the men's soccer team would, on average, expect to play 1.1 days per week. So, in other words, we would say that the mean mu is equal to 1.1. Another one. So let's go back to the random variable we looked at in 4.1 regarding the number of times a newborn baby wakes its mother after midnight. So here are the outcomes: 0 times per night or 5 times. And here were the probabilities that we figured out in decimal form. And if we find their products, 0 times the probability of x, we get 0, 11 out of 50, 4 out of 50, 27 out of 50, 16 out of 50, and 5 out of 50. And if we were to add those, the expected number of times on average that a baby's expected to wake their mother after midnight is 2.1 times. Okay. Now, to find the expected standard deviation, we're going to use this formula. You're going to take the probability of the outcome from, this would be x1, y1. This is x1 star y1. So you're going to take y1, the probability, and you're going to multiply it by x1, subtracting the mean. And we know the mean, so we have to actually enter this, 2 minus 2.1. And then square that. And we want to total that. I'm going to show you how I did this in Desmos. So here are the probabilities. Here are each of the outcomes, 0, 1, 2, 3, 4, and 5, subtracting the mean of 2.1, squaring that difference, and then we're going to add up these totals. And there's our standard deviation, 1.05. So a baby is expected to wake up their mother on average 2.1 times, give or take 1.02 times per night. And I'm going to share my screen to show you how I did this in Desmos. This link is under the Math 201 expected value link underneath our lesson video. So here's our X1, our probabilities. Then here's our product of X1 and Y1. And we add those up, and that's where we get the values. This is different data I'm going with in the next example. So I can show you there. So let's go through the next example together. It's the hospital researchers interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. We looked at this data in lesson 5.1 as well. And we are going to, this is what I have up that you pulled up in Desmos, X1 and Y1. This is going to be X1 star Y1. And when we multiply these, this is what we get. And we tell Desmos to add these together. The expected value, or the number of times a patient is expected to ring the nurse out of 50 patients, would be 2.32 times when we were to add these. Then, to create our standard deviation, we're going to take the probability, so 4 out of 50, or 0.08, and we're going to take the outcome of 0 and subtract the mean of 2.32 and square that. And then the next probability, which is 0.16, and take 1 minus the mean and square that. And then the next one is 0.32 and 2 minus the mean and square that. And then the probability there, 3, subtracting 2.32 and square that, 0.112. And 0.04. And this is actually being done in Desmos. I'm going to go show you that. And so there are those products, and then we're totaling that down here, taking Y1 times the difference of the X1 outcome, subtracting the mean squared. So on average, a post-op patient wakes up or rings their nurse 2.3 times, give or take 1.2 times. We've got a few more examples here for you. Example 4 says, suppose you play a game of chance in which 5 numbers are chosen from 0 through 9. A computer randomly selects 5 numbers from 0 to 9 with replacement. You pay $2 to play and could profit $100,000 if you match all 5 numbers in order. That means you get your $2 back plus $100,000. Over the long term, what is your expected profit of playing the game? To do this, we're going to set up an expected value table. And so an expected value table down here is how I set mine up, is I list the outcomes in words. So we could have a loss of a negative $2 if we don't win, we lose our $2 bet, or we have a profit. And so X is the numerical loss or profit. So numerically we would lose $2, or numerically we would profit $100,000 over getting our money back. So profit is always what you've made over getting your money investment back. The probability of these happening is up here. So to win, you must get all 5 numbers correct in order. The probability of choosing one correct number is 1 out of 10. Because there are 10 numbers, you may choose a number more than once. The probability of choosing all 5 numbers correctly and in order is this. So 0.00001. So that's the probability of winning right here. And then the complement of that, 1 minus that, is the probability of losing. So our P of X has to add to 1. And then we're again going to take, so these would go into X1 in Desmos, these would go into Y1, and then we're just going to multiply X1 times Y1 and total them. So when we do that, it looks like on average you would expect to lose about $1 for each game that you play. However, each time you play, you either lose $2 or you profit $100,000. The dollar is the average or expected loss per game after playing this game over and over. So remember, it's the expected profit or losses over long-term time. Let's do a couple of these on our own. The example says, suppose you play a game with a spinner. You play each game by spinning the spinner once. The probability of red is 2 out of 5, the probability of blue is 2 out of 5, and the probability of green is only 1 out of 5. If you land on red, you pay $10. If you land on blue, you don't pay or win anything. If you land on green, you win $10. Complete the following expected value table. So it doesn't look like we pay to play at all, but we have some values in our profit and our probability here. So the outcome of red, what is our profit there? If you land on red, you pay $10. So our profit's going to be a negative 10. If you land on blue, you don't pay or win anything. So it's 0. And if you land on green, you win $10. Okay. The probability of getting a red is 2 out of 5. The probability of getting a blue is 2 out of 5, and the probability of getting a green is 1 out of 5. So when we multiply this would be in Desmos, this would be our X1 and our Y1. When we multiply those, we get a negative 20 over 5, which would be a negative $4 for the red. Here would be 0 times 2/5 or 0. We don't win or lose. And then here would be 10 times 1/5 or 2. And so the expected profit or loss would be adding a negative 4 plus 0 plus 2 or a loss of $2. So overall, if you were to spin this game 10, 20, 100, 1,000 times, overall, you would expect to lose $2 on average. Look at example 6. Example 6 says, on May 11, 2013, the probability that moderate seismic activity, one moderate earthquake, would occur in the next 48 hours in Iran was about 21.42%. Suppose you make a bet that a moderate earthquake will occur in Iran during this period. If you win the bet, you win $50. If you lose the bet, you pay $20. Let X be the amount of bet profit from the bet. So the probability of winning, which means that an earthquake will occur, they said was about 0.2142 in decimal form. The probability that an earthquake will not occur is 1 minus that. Which is 0.7858. If you bet many times, will you come out ahead? That's the question. Explain your answer in a complete sentence using numbers. What is the standard deviation? So let's first look at the outcomes. If I win, the outcome is $50 profit. So that's a positive 50. If I lose, I pay 20. So that's a negative 20 for me numerically. The likelihood of those happening, the probability of winning, we said was 0.2142, and winning was losing was 0.7858. Make sure that they add to 1. Then when we multiply, this will be x1 in decimals and y1 in decimals. When we multiply them, we get 10.71 and a negative 15.716. And so adding the product column of x1, y1 is our expected value. So on average, we would expect to lose about just over $5, $5.01. Now, the standard deviation is going to be taking 50, subtracting the average, but our average is a negative 5.006. Squaring that times our probability of 0.2142. And then over here is a negative 20, subtracting that negative 5.06 squared times 0.7858. And then just multiplying what those come out to be using decimals. So if we add our standard deviation, so if we add these two columns down here, we get our standard deviation of about 28.72. So on average, we're expecting to lose about a loss of about $5.01 loss, give or take about $28.72. So it's not really a good bet.